Welcome back, efficient learners and AI practitioners. Today, we're diving into one of the most practical and powerful techniques in modern machine learning, transfer learning. Have you ever wondered how AI models can learn new tasks so quickly? Or how you can build powerful models even with limited data? Transfer learning is the secret sauce that makes this possible. In this video, we'll explore how you can leverage existing knowledge to accelerate your AI projects, save resources, and achieve state-of-the-art results. Let's discover how to stand on the shoulders of AI giants and build smarter, faster models together. Imagine if every time you needed to learn something new, you had to start from scratch, just like a baby. That's how traditional machine learning works. Each new task requires building a model from the ground up. Transfer learning changes the game by allowing models to leverage knowledge from previous tasks, making the learning process much faster and more efficient. It's similar to learning to drive a car after knowing how to ride a bicycle. You already understand balance and steering, so you only need to learn the differences. This approach saves time and effort, making AI development more accessible. Transfer learning is a machine learning method where a model developed for one task is reused as the starting point for a model on a second related task. The core idea is simple. Knowledge gained from solving one problem can be applied to a different but related problem. This approach saves both time and computational resources, especially when you have limited data. Think of a medical student who already knows biology. They don't start from scratch when learning surgery. Instead, they transfer their existing knowledge to the new domain, making the learning process much more efficient. Training large models from scratch is expensive and often impractical, especially when real-world problems have limited labeled data. Pre-trained models capture general patterns from vast datasets, allowing for faster deployment and iteration. By leveraging transfer learning, you can build high-performing models without the need for massive resources. This technique democratizes AI development, making it accessible to more people and organizations. With transfer learning, you can achieve better results in less time, opening up new possibilities for innovation and problem-solving. The basic process of transfer learning starts with a pre-trained model, often trained on a large dataset like ImageNet. You remove the top task-specific layers and add new layers tailored to your specific task. Then, you fine-tune the model on your smaller dataset. There are two main approaches: feature extraction, where you freeze pre-trained layers and only train new classification layers, and fine-tuning, where you unfreeze some pre-trained layers and continue training on new data. This flexibility allows you to adapt powerful models to a wide range of tasks efficiently. Feature extraction and fine-tuning are the two main strategies in transfer learning. In feature extraction, you freeze the pre-trained layers and use them as fixed feature extractors, only training the new classification layers. This approach is faster and works well for very similar tasks. Fine-tuning, on the other hand, involves unfreezing some of the pre-trained layers and continuing training on new data. This allows the model to adapt its learned features to the specifics of your new task, making it ideal for moderately different tasks. Choosing the right approach depends on your data and goals. Transfer learning can be applied in various scenarios, using the same domain but a different task, a different domain but the same task, or even a different domain and a different task. For example, a model trained to recognize animals in photos can be adapted to identify medical conditions in X-rays. This versatility makes transfer learning a powerful tool for tackling a wide range of machine learning challenges, regardless of the domain or the amount of data available. One reason transfer learning is so effective is that early layers of deep learning models learn universal features, such as edges and textures in images. These features are useful across many tasks, so only the later layers need to be retrained for specific applications. This means you don't have to start from scratch, saving time and computational resources. By leveraging these general features, transfer learning enables models to quickly adapt to new tasks with minimal data and effort. Transfer learning offers several statistical advantages. It helps models generalize better when you have limited data, reducing the risk of overfitting. Training becomes more stable, and you can achieve better performance with fewer examples. These benefits are especially important in real-world scenarios where collecting large, labeled datasets is challenging. By building on existing knowledge, transfer learning makes it possible to create robust models even in data-scarce environments. Transfer learning dramatically reduces training times and computational costs. Since much of the learning has already been done on large datasets, you only need to fine-tune the model for your specific task. This means less energy consumption and the ability to train models on smaller hardware. For many organizations, this makes advanced AI development feasible without the need for expensive infrastructure, opening the door to innovation for more people. Beyond technical benefits, transfer learning offers practical advantages. It enables faster prototyping and experimentation, lowers data collection costs, and provides access to state-of-the-art architectures. By making advanced AI tools more accessible, transfer learning democratizes AI development, allowing more people to participate in building innovative solutions. This practical edge is why transfer learning has become a cornerstone of modern machine learning workflows. In computer vision, transfer learning is widely used. Popular base models like ResNet, VGG, and EfficientNet are trained on massive datasets such as ImageNet. For new tasks like medical image analysis or satellite imagery, you simply replace the final classification layer and fine-tune the model. This approach allows you to achieve high accuracy with much less data, making it ideal for specialized applications where labeled data is scarce. Natural language processing, NLP, has also benefited greatly from transfer learning. Models like BERT, GPT, and RoBERTa are pre-trained on large text corpora and can be adapted for tasks such as sentiment analysis or spam detection by adding task-specific layers. This method allows you to leverage the deep understanding these models have of language, making it easier to build powerful NLP applications with less data and effort. Audio processing tasks, such as emotion detection or music classification, also benefit from transfer learning. Models trained on large audio datasets can transfer their knowledge of acoustic features to new tasks. By fine-tuning these models, you can achieve impressive results even with limited labeled audio data, making it easier to develop applications in speech, music, and sound analysis. Transfer learning isn't limited to a single domain. You can use image models for video analysis, text models for code understanding, or speech models for music generation. This cross-domain flexibility allows you to tackle a wide variety of problems by leveraging existing models, making transfer learning a versatile tool in your AI toolkit. A great real-world example of transfer learning is in manufacturing. A model trained to recognize everyday objects can be fine-tuned to detect manufacturing defects with only hundreds of examples, instead of millions. This approach saves time, reduces costs, and enables rapid deployment of quality control systems, making manufacturing processes more efficient and reliable. When implementing transfer learning, choosing the right pre-trained model is crucial. Make sure the model's input dimensions match your data, and consider the trade-off between model size and accuracy. Check the licensing and usage terms to ensure compliance, and evaluate the computational requirements to make sure the model fits your available resources. Selecting the right model sets the foundation for a successful transfer learning project. Proper data preparation is key for successful transfer learning. Pre-process your data in the same way as the original training data. Handle class imbalance in your target task, and ensure appropriate train validation splits. For small datasets, data augmentation techniques can help increase diversity and improve model performance. Careful data preparation helps your model adapt smoothly to the new task. There are several strategies for fine-tuning pre-trained models. Progressive unfreezing involves gradually unfreezing layers, while differential learning rates apply different rates to different layers. Layer freezing keeps early layers frozen, and selective fine-tuning focuses only on specific layers. These techniques help you adapt the model efficiently to your new task, balancing performance and computational cost. When fine-tuning, it's important to use lower learning rates than in initial training. Carefully select batch sizes and apply appropriate regularization. Early stopping can help prevent overfitting, especially when working with small datasets. These hyperparameter choices ensure that your transfer learning process is stable and effective, leading to better model performance. Transfer learning has revolutionized healthcare applications. Models pre-trained on ImageNet have been used for chest X-ray diagnosis, skin cancer detection, and medical image segmentation. In drug discovery, transfer learning accelerates the identification of promising compounds. These advances improve diagnostic accuracy, speed up research, and make cutting-edge healthcare more accessible. In the world of autonomous vehicles, transfer learning enables object detection, road condition, classification, pedestrian behavior prediction, and traffic sign recognition. By adapting general models to specific vehicle environments, developers can build safer and more reliable self-driving systems, even with limited labeled data. This accelerates the development and deployment of autonomous technologies. E-commerce platforms use transfer learning for product recommendation systems, visual search, fraud detection, and customer sentiment analysis. By leveraging pre-trained models, these platforms can offer personalized experiences, detect suspicious activity, and understand customer feedback more effectively, all while reducing the need for massive labeled datasets. In agriculture, transfer learning powers crop disease detection, yield prediction, soil quality assessment, and pest identification. By adapting models trained on general images to agricultural tasks, farmers and researchers can monitor crops more effectively, predict yields, and respond quickly to threats, improving food security and sustainability. Manufacturing benefits from transfer learning through quality control, defect detection, predictive maintenance, and supply chain optimization. By fine-tuning models on specific manufacturing data, companies can automate inspections, predict equipment failures, and streamline processes, leading to higher efficiency and reduced costs. Some of the most popular pre-trained models in computer vision include ResNet, EfficientNet, VGG, and MobileNet. In natural language processing, BERT, GPT, RoBERTa, and DistilBERT are widely used. For multimodal tasks, models like CLIP, DALL-E, and Vision Transformers are leading the way. These models provide a strong foundation for transfer learning across a variety of applications. Transfer learning works best when the source and target tasks are related. The source dataset is larger than the target dataset, and the pre-trained model is high quality. It's also ideal when computational resources are limited. Following these best practices ensures that you get the most out of transfer learning, achieving strong results with less effort. Some common mistakes in transfer learning include using unrelated pre-trained models, not adapting pre-processing steps properly, overfitting on small target datasets, and choosing the wrong layers to fine-tune. Being aware of these pitfalls helps you avoid wasted effort and ensures your transfer learning projects are successful. Advanced transfer learning techniques include domain adaptation, which handles domain shifts, multitask learning for learning multiple tasks simultaneously, meta-learning for learning to learn across tasks, and knowledge distillation for transferring knowledge to smaller models. These methods push the boundaries of what transfer learning can achieve, enabling even more flexible and powerful AI systems. The future of transfer learning is bright, with exciting directions like automated transfer learning, cross-modal transfers, few-shot and zero-shot learning, and continual learning systems. These advancements will make AI even more accessible and capable, allowing models to adapt to new tasks with minimal data and ongoing learning. As the field evolves, transfer learning will remain a cornerstone of practical AI development. Transfer learning has democratized AI by making state-of-the-art performance accessible to everyone. Instead of needing massive datasets and computational resources, developers can now build powerful models by building on existing knowledge. As AI continues to evolve, transfer learning will remain a cornerstone technique, enabling faster innovation, reduced costs, and broader accessibility. Remember, why start from scratch when you can stand on the shoulders of giants? Embrace transfer learning to boost your AI projects and unlock new possibilities.